website of Chipworks, which is a company which publishes cross-section of devices and systems. A very nice website if you're interested. This is the silicon. And this is the cross-section, which means the current is going, the gate is around the FinFET, and the inversion layer is here. So, and you can think, if you look at this device, you start to see, I go to, this is another picture of the FinFET structure. And if you go to sort of very high resolution, you see the problem that I told you about this problem. This is the silicon. Let me switch color to white. This is the silicon. This is the oxide. And this is the gate. And you can see between the width of this fin is, you cannot neglect the atoms. It's not much bigger. You have 20, 30 atoms. And this is current technology. In 2-3 years, we have much better technology. I'm going to show some even smaller devices soon. So in this TEM image, which was taken by an FEI Osiris, which is a really powerful transmission electron microscope, you can see the lattice image of a fin in an NMOS transistor. And this is the channel are oriented in the 111 direction. By the way, this was 2012. So this is a 9-year-old image. The FinFET itself looks like this. This is the fins, and the gate is around it. However, in future devices, people say if we make the gate around the fin, why not making the gate surrounding the device? This is called GAA, gate all around. This is like the dream of the device engineer. Because if you make this device, then we don't have this device will have a better performance than this device because we control we can have a much better switch. Little problem is how to do it. So multi-gate FETs is one of the future technologies, or one of the most promising future technologies. We have improved the electrostatics, steeper subthreshold slope. We still have problems with parasitic resistance and capacitance, but the advantages are so impressive, so we think this is the direction. So what is in the future of devices? We do the fin. If you think about it, the fin means sorry, I'm using the white. This is like, if you think about this is the fin, and the gate is like this. I'm sorry. So the conduction is in this direction. And this is tri-gate, when we have the fin and the gate is on top. Sometimes because of process, it looks more rounder than square. The omega gate is an experiment to make the gate really rounded. And all around gate, if you can have the gate and the current is flowing in this direction. You can think about this as a tube, when the conduction is inside the tube and the gate is all around it. If you're going to make this device, you will get better performance. So how it looks in real life, this is presented in 2021, which was presented a few months ago in the ISCC conference by the chairman of a company in Taiwan called TSMC. And he presented an image of, this is how it looks in real life. This is the FinFET featuring high mobility channel. And this is a cross section of the fin. And they have a high mobility channel, or they use some techniques to get this FinFET, the semiconductor, this is a kind of a TM image in the center of the fin, and they claim to have a high mobility in the fin, and this is how it looks from in real life. And this is as you can see, each one here is a transistor, and this is the first layer of the gate. This is the front end of the circuit. Now, if you think about it, I want to reiterate that this is the fin, and we have the channel, and the energy, we have the source and the drain, and we have the barrier, and how we control the switch. We make this barrier high, or we can make it low. If we make it low, electrons are jumping. If we make it high, they are supposed not to jump. However, they can tunnel. And 3 nanometer is what we believe is kind of the practical barrier before we start to have direct tunnel current. So this is, I would say, this is a barrier which is really getting closer. And this is again from the same lecture of Mark Liu from TSMC, where you can see that people are, this is what's called nanosheet transistor. This is, let me annotate so I can get, this is the gate around, so this is the gate. Sorry, this is silicon, and the conduction is kind of in this direction, and the gate is around it. And the gate is around it, and you have the NMOS device and the PMOS device, and you have a complete CMOS device. These operations are expected to work at 0.46 volt. One of the things we want to do in VLSI is to reduce power, and power is proportional to the capacitance of our devices, the voltage square times the frequency. So if you want to make low power, you want to reduce the capacitance, reduce the voltage, but frequency, we don't want to make it too large. Oops, sorry, by mistake, I go back. I hope you can see it again. Sorry, by mistake, I stopped sharing and I continue sharing. So what is in the future? The design technology co-optimization, or this concept, the new concept now is that since we cannot scale too much, so we are all aware of the limit below 10 nanometers CMOS. And however, transistor density is expected to continue increasing to a similar pace of about 45% density increase per node. This is due to the R&D, and the new concept is design technology co-optimization, or DTCO, and improvements in electronic design automation, or EDA. The meaning of this word that we don't do just scaling of the technology or just improvement in the layout, and we do co-optimization of both the layout, and this is technology dimensional. In the past, what we just did the technology dimensional scaling. This is for example, this is taken from Intel. This is their, I think, 90 or 65 nanometer technology, and this is the 22 nanometer or less, and we just make devices smaller and smaller. And then today we think about design technology co-optimization, where we do optimization of the pitch of the device, design constructs to increase density, performance, and reduce power. So when people are doing layout, they do it co-optimizing, they do it together with optimizing the technology. And we think that the next, this is not happening today, the next is co-optimization of the system architecture, that when we do the design of the system, we work together with the engineers in the fabrication. Because today the way it works, we have fabs making this. You design it in one place, and many companies are fabless, they design it, then they send it to manufacturing. It seems like in the future, or in the near future, or even now, people start to understand that you have to work together. The design and manufacturing should be together. And this is the new concept, the DTCO, which people are talking, this is the new buzzword now. And the growing DTCO contribution to density, because for example, in an intrinsic scaling, this is your device, node number, and you just make them smaller. You make them smaller, you make it denser. In DTCO, it's not, you scale your devices, but you also change the design. For example, in this specific design, you move the contact. In this specific design, you move the contact from here, you move it to here. So you not only you change the technology, but you also change the design. And intrinsic scaling was dominant down to 10 nanometer. In 7 nanometer, we assume that 25% is due to interaction between design and technology. In the 5 nanometer, it's 40%. In the 3 nanometers, like 50-50. Intrinsic scaling and DTCO will be together. So this is the way, one of the near future things in design, which means, by the way, for us as professors teaching VLSI design, and I'm teaching VLSI design, I'm teaching VLSI technology, and I'm teaching VLSI devices, which means we need the students in VLSI design to understand the process, and not only to understand, to be experts in the process, also to be experts in the physics of the devices, which means the future VLSI designer, or the top one, will have to be capable, we should teach them both technology and physics and design. So it's not enough just to teach design. This is the moral of the story for our cloud. And I apologize, I lost, okay. Okay, so this is taken from the news. I took it from one of the websites and one of the newspapers. The Taiwanese semiconductor manufacturing detailed characteristics of the future 3 nanometer process node. And they have the roadmap for the 5 nanometer successful to form the NFP and N4 process node. And they gave this picture. I mean, I cannot guarantee that this is the 5 nanometer. This is what I took from the website. But if you go to the TSMC website, which is, this is the Taiwanese company, which are the leaders today in technology. So I took them as the, as a kind of comparing to other methods. N7, this is the 7 nanometer, N5 is the 5 nanometer, N3 is the 3 nanometers. And you can see that by switching from 7 nanometer to 3 nanometer, we get 25 to 30% improvement in power, 10 to 15% improvement in performance, area 60, almost time 60%, density is better, and the 3 nanometer hopefully will be in 2022. So this is future technology. Today manufacturing is 5 nanometer. So one of the laws of this kind of lectures, you cannot give a lecture on future VLSI without showing Moore's law. But I decided to give you kind of a sophisticated Moore's law. Moore's law, you plot the variable that you want in a log scale, and you plot the year in a linear scale. And if you put the number of transistors, you can see that the number of transistors is increasing. I have to switch to black one. You see it's increasing along this line. Now, if you go to the single thread performance of chips, you see something surprising. You see that about 2010, they reach the saturation, which means you get more transistors, more devices, but you don't get better performance from your chip. And the frequency of our devices was stuck. As you know, this is megahertz, 3, 4, 5 gigahertz. And the power was stuck at about 100 watts per centimeter square. However, the number of cores is going up, and recently it's also not going up very rapidly. So what happens to Moore's law? We got more devices, but we don't get better performance. So something is happening. Another way to look at it